Okay, thankfully we were able to go over this in class together before I was gone, but a quick review as far as parametric curves, parametric equations. What we're basically doing with a parametric equation is we're taking our typical function and we're breaking it into two separate functions, one just for the x component and one just for the y component. In order to do that, we add in a third variable, t, which is considered the parameter of the function. And we will typically evaluate these functions over an interval I of t values. The thing to remember is, from a terminology standpoint, is when it asks for the parameterization of a curve, the parameterization of the curve is going to be a couple of things. It's going to be the parametric equations and the interval. What we'll do is we will work on through the beginning examples that we've already gone through in class, but just as a refresher, and then we'll do part 2, which will lead us into new material as well. Okay, so let's talk about the first example, which is just trying to find, for the given parameter interval. Okay, so in this example, we're given the parametric equations that x equals t squared minus 2 and y equals 3t. So we're going to now use those two equations to generate the graphs based on the intervals set forth in A, B, and C. So first off, we'll look at A together. You can see the actual graphs are already given to us underneath, but we'll generate the values for graph A, and then I'll let you try to do B and C on your own. But first off, so let's go ahead and make a table having our t values that give us our x and our y's. And so looking at it from -3 to 1, we'll just take integer values, even though really this spans all values, but we'll create some data points when t is -3, -2, -1, 0, and 1. So when t is -3, plugging that into the x equation, we get -3 squared is 9, minus 2 is 7, and plugging into the y equation, we get 3 times -3 is -9. And if you notice, we have the point 7, -9 on our graph. So, all right, so we'll continue with the other points. -2 for t. -2 squared is 4, minus 2 is 2. And then 3 times -2 is -6. -1 squared is 1 minus 2 is -1. And -1 times 3, -3. 0 squared is 0 minus 2, -2. 3 times 0 is 0. And then 1 squared is 1 minus 2 is -1, and 1 times 3 is 3. So we now have our values, 0.7, -9, the 0.2, -6, the point -1, -3, the point -2, 0, and the point -1, 3. So that is how we use the parametric equations to generate graphs. Okay, in the next example, we see how to eliminate the parameter. Eliminating the parameter is basically going the other direction. So here we have a parametric equation where the x value is 1 minus 2t and the y value is 2 minus t. Our interval is -infinity to infinity, and so we solved the first equation for t. So if you notice, all we really did here is we took the first equation and we solved it for t. So we subtracted 1 from both sides. Well, really, we decided to make the -2t positive, so they added, make notes here, we added 2t to both sides and subtracted x. So plus 2t and minus x from both sides gets us to our next step. At that point, we simply divided or multiplied by a half to get rid of the 2, and we wind up with t equals 1/2 times 1 minus x. Now, this is just a typical system of equations at this point. We can now substitute this into the y equation for t. So 2 minus t becomes 2 minus 1/2 times 1 minus x. And from there, distribute and combine your like terms. So 2 minus 1/2 plus 1/2 x becomes 0.5x plus 0.5, and we now have the equation of a line, as you can see over in the figure on the left, that came from this parametric equation. So this parametric equation and this equation in slope-intercept form, they are equivalent equations based on the interval -infinity to infinity. Interestingly enough, if we change that interval, we now have a way to graph a line segment instead of a full-out line. And that's something that in our notation that we've done so far, unless we did piecewise functions, we didn't have that ability. But now using a parametric function, we can graph segments as well as lines. Okay, we're going to try this again. The app has been crashing left and right, so we're going to see if we can get through this example for you guys. So in this example, again, we're going to eliminate the parameter to get it into a normal like y equals function. In this case, it is much easier to eliminate or to isolate the t in the y equation instead of the x equation like we did in the last example. So looking at that, y equals 3t, you can easily see that if you divide by 3, t is going to equal y over 3, if we can get that to right. So now we simply substitute that into the x equation, and x is going to equal y over 3 squared minus 2, which when we square that, x equals y squared over 9 minus 2. So if we add 2 and multiply by 9, we get that 9 times x plus 2 equals y squared. Now, of course, we can further simplify that and say then that y is going to equal plus or minus the square root of 9 times x plus 2, which, again, can be further simplified to that is a y. Let's clean that up just a little bit for you. Y equals plus or minus 3 square root of x plus 2. And that's it. So this is the equivalent of the parametric curve. X equals t squared minus 2 and y equals 3t. Granted, that also means that for the parametric curve would have an interval of negative infinity to infinity, whereas this has, we could figure out the domain and range restrictions based on this. So there you have it. Okay, so here we've got another eliminate the parameter problem. This one is a little bit contrived. You'd have to definitely be thinking along the right lines to have the chance at actually solving this. But if we graphed it first, it would actually be quite helpful, because you'd see a graph that looks like it could perhaps be a circle with centered at the origin with a radius of 2, and therefore that lets us kind of lead us in a certain direction. So as we look at this, if knowing that it looks like a circle, the equation for a circle is, x squared plus y squared equals r squared. So it makes me want to go and say that x squared equals 4 cosine squared t, and y squared equals 4 sine squared t, and therefore x squared plus y squared would equal 4 cosine squared t plus 4 sine squared t, at which point we can factor out a 4, leave ourselves with cosine squared t plus sine squared t, and of course we quickly recognize the cosine squared plus sine squared is the Pythagorean identity, which equals 1. Therefore 4 times 1 is just 4, and we indeed have x squared plus y squared equals 4, which would be the equation of a circle centered at the origin with radius 2. Okay, so finding the parametric equation for a line. All right, see if you stick with me on this. We are going to, first off, we're going to create a vector in the direction of line AB. Knowing that we have points A and points B, and they are given to us here and here, we're going to go ahead and create a vector AB, which, by putting a third point, the point P, just arbitrarily on that line. We don't know what x and y are, we don't care, we just know that point P lies on AB. By doing that, we can see that the vector OP, so this is the vector OP, is going to equal the vector sum of OA. My pen is tripping. Let's try that again. The vector OA plus the vector AP. But what we just said a moment ago was that AP, we put P somewhere on AB. So AP is in the same direction as AB, which means we could rewrite AP as some scale factor t times the vector AB. Now, that's good news because we have an initial and a terminal point for AB. That means that I'm going to go up here to the side. I can say that AB equals the vector, and I can just simply do my components, 3 minus negative 2 and 6 minus 3, and I get that that vector is the vector 5, 3. Now, OA is the vector negative 2, 3. OP is the vector XY. When we put all of that together, OP is the vector X, Y, and it equals OA, the vector negative 2, 3, plus T times the vector AB, which is 5, 3. Now, knowing we can multiply that in and we get the vector 5t, 3t, and then we're going to add our vectors. That means that we get xy equal to negative 2 plus 5t and 3 plus 3t. Well, that gives us our parametric equation. The x value in our parametric equation is going to equal negative 2 plus 5t. The y value will equal 3 plus 3t, yielding x equals negative 2 plus 5t, y equals 3 plus 3t, and of course this is a line, it goes on forever, therefore we will say that t is the interval negative infinity to infinity, and there you have it. There's our answer. Okay, so here we've got example talking about simulating projectile motion. Now this is a little bit different than projectile motion problems you've done in the past. Here we're given, the situation: distress flare shot straight up from a ship's bridge 75 feet above the water with an initial velocity of 76 feet per second. Graph the flare's height against time. And that is something that typically we think of projectile motion problems as parabolic in nature. And here we'll see this comes out slightly different as parametric. So given the height of the flare above the water each time, and simulate the flare's motion at each length of time: 1 second, 2 seconds, 4 seconds, 5 seconds. So first off, we have to come up with what our typical equation would be to model this, which we would use the following. We would say that y equals, and then we've got gravity, negative 16 t squared plus initial velocity, 76t, plus initial height, 75. Okay, now that in and of itself, great, there's our equation. However, if we now want to graph the height against time, we're going to use parametric equations and simply set our x equal to t. That'll be our first x. And then we'll set our first y equal to negative 16 t squared plus 76t plus 75. Now we're going to do a second parabolic, or a second parametric equation, and we're going to let x2 be 5.5. Now at first 5.5 might seem kind of random. Y2 will still be the same equation, negative 16, it's not like my 6's, t squared plus 76t plus 75. But the reason why the 5.5 is there is because our graphs won't intersect at this point because we are done looking at the other graph at 5 seconds. So this being 5.5 means it will be graphically it'll appear after the graph. Okay, so now I've added the graphs, and you can see that here is when t equals 1, and we've got the projectile going up, the flare going up, and this also just shows us where an x is not changing. This is simply showing the height going up, up, coming down, down. So notice the blue mark on this graph and the location on the parabola are always the same. Top, top, midway up, midway up. And so that's what these two equations are showing. This first set of equations here is what's drawing the curve. That is when t is 1, t is 2, 4, and 5, just like the question asked. And the second equation is simply showing the height of the flare above the water at each time. So this is simply simulating the flare's motion. It's going up, going up, coming down, and it's down. That's all there is to that one. Okay, before we move on to the next example, we'll take a look at this that we'll use in the next example. So we talked about in example 8, we modeled the motion of a projectile that was launched straight up, but now we're going to look at things that are at different angles. And so here's an example of, suppose a baseball is thrown from a point y sub 0 feet above ground level with an initial speed of v sub 0 feet per second at an angle theta with the horizontal. The initial velocity can be represented by the vector right here, v equals v sub 0 cosine theta, v sub 0 sine theta. Keeping in mind that this would be the x or horizontal component, this would be the y or vertical component. And so when we break this into parametric equations, the x component of the parametric, which is right here, is simply going to be the x component of the initial velocity times t for time. So we're just taking this and plugging it in there, and then the y component of the projectile motion equation is, again, the y component from initial velocity, and that is inserted into the kind of standard vertical projectile motion equation that we use, the negative 16t squared plus initial velocity times t plus initial height. So here is, again, due to gravity, initial velocity, initial height. And that's what comes up with our parametric equations. So now we'll go ahead and use that in our next example. Okay, so here we're given example 9, which will use what we just talked about. Kevin hits a baseball 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? And so we need to first off figure out what is the parametric equation for this. And we said that we can simply use the initial velocity and the x component of that vector for the x equation in our parametric equations. So we would say x equals (150) cosine of 18 times t. And then the y equation would be the familiar negative 16t squared plus, and now the y component of our initial velocity vector, 150 sine of 18 t plus the initial height of 3. Okay, so once we have that, we should be able to, I'm going to just go ahead and try to move that in a moment to rewrite it. Okay, and written a little bit neater is the equations there. Okay, so after we can kind of mess around with this a little bit, we'll see that the ball would actually reach the fence, because here you have the x component, and here you have the y component. So we want to know when is x going to equal 400, and so we should be able to do a little bit of math here and say 400 equals 150 cosine 18t, and therefore 400 divided by 150 cosine 18 should equal t. Taking a moment to calculate that, we get that t would equal about 2.8 seconds. And so plugging 2.8 into the y equation, we should get a solution of 7.35. So this is the y piece. So at 2.8 seconds, the height of the ball is only 7.35 feet. Therefore, it will not be clearing a 20-foot wall. You can also see this graphically right there, and to do that, to have the wall actually be there, we could do similar to what we did earlier and just generate an x equation where the x is always going to be the constant, which would be the 400 feet away. So at 400 is what x always is, and the y is still going to be the y equation, and it would simply track the height of the ball over time, and you would see that the ball at that time is going to be right there.